The developmental combat aircraft platform known under the industrial designation SAC J50 represents a fundamental and comprehensive reconceptualization of air dominance platform design, moving beyond the evolutionary path established by previous generation fighter aircraft and embodying a set of deeply integrated and synergistic technological choices aimed at achieving a new level of capability in highly contested operational environments. Its entire architectural philosophy, as discerned from its physical configuration and the logical progression of its test campaign, is predicated on the principle of achieving a decisive advantage through a combination of pervasive low observability, persistent high-speed performance, and novel control authority, thereby creating a system designed to operate with impunity in airspace saturated with advanced integrated air defense systems and peer-level adversary aircraft. The cornerstone of this design philosophy, and its most visually distinctive feature, is the implementation of a fully tailless combat airframe. This configuration represents a radical departure from conventional aircraft design, which has relied upon vertical and horizontal tail surfaces for fundamental stability and control. The removal of these surfaces is a direct and profound response to the physics of radar detection. Vertical stabilizers, in particular, present large, perpendicular surfaces that act as highly efficient retroreflectors for a wide range of radar frequencies. Their elimination, coupled with the absence of horizontal stabilizers, drastically reduces the number of major radar scattering sources on the airframe. This forces the overall platform into a blended body and flying wing morphology, which is intrinsically more amenable to stealth shaping. This shaping involves the meticulous alignment of all leading and trailing edges, on the wing, body, and control surfaces, to a narrow set of angles. This precise geometric discipline ensures that any incoming radar energy is not scattered randomly but is instead reflected in a controlled manner, channeled into a few narrow beams away from the receiving radar, thereby reducing the probability of detection to an extremely low level. This foundational stealth approach is further augmented by other observable features. The engine air intakes utilize a diverterless supersonic inlet design, which employs a carefully contoured compression bump instead of complex mechanical ramps and boundary layer diverters. This fixed structure manages the airflow to the engine fans while effectively shielding the highly reflective compressor faces from direct radar illumination across a broad frontal sector. The entire airframe surface is also likely treated with specialized radar-absorbent materials and coatings, which convert incident radar energy into heat rather than reflecting it, working in concert with the platform's shape to minimize its radar cross-section from all aspects. The profound aerodynamic challenge posed by the removal of all traditional tail surfaces necessitated a revolutionary solution for flight control and stability. This solution is engineered into the heart of the aircraft's propulsion system. The platform is powered by two next-generation low-bypass turbofan engines, which are characterized by their high thrust-to-weight ratios and suitability for sustained high-speed flight. The critical innovation lies in the integration of two-dimensional thrust vectoring nozzles at the exhaust of each engine. These nozzles are not circular but feature a rectangular, variable geometry structure that allows the entire exhaust plume to be deflected en masse in the vertical plane. This capability to vector thrust is not merely an enhancement for agility, it is an absolute prerequisite for the aircraft's basic controllability. By differentially articulating these nozzles, the flight control system can generate powerful pitching moments, effectively substituting for the function of missing elevators and a rudder. This provides direct control authority that is independent of airspeed and atmospheric density, ensuring the aircraft remains controllable at very low speeds during approach and landing, as well as at extreme altitudes where the thin air renders conventional aerodynamic control surfaces nearly useless. This integration of propulsion and flight control creates a tightly coupled system where engine output is directly translated into vehicle maneuvering, enabling rapid changes in attitude and potential post-stall maneuvers that would be impossible for a conventionally configured aircraft. The synergistic interaction between the exceptionally clean, low-drag tailless airframe and the high-thrust, vectoring propulsion system enables the aircraft to access a key performance regime known as supercruise. This is the demonstrated capability to maintain sustained, level flight at supersonic speeds without any requirement to engage the engine afterburners. Afterburners, while providing a substantial boost in thrust, are phenomenally inefficient, increasing fuel flow rates by several 100% for a marginal gain in thrust, thereby drastically reducing an aircraft's combat radius and on-station time. The J-50's design, with its minimal aerodynamic drag and modern engines optimized for high dry thrust, is fundamentally architected to overcome the transonic drag hump and accelerate to supersonic speeds using only its primary engine cycle. The tactical implications of supercruise are multifaceted and profound. It allows the platform to rapidly close vast distances to intercept time-sensitive targets, to reposition quickly across a wide battlespace, and to impart significantly higher initial kinetic energy to its launched missiles, extending their effective range and no-escape zone. Furthermore, supercruising without an afterburner substantially reduces the platform's infrared signature, as the most intense and detectable heat source on an aircraft is the plume from an active afterburner, thereby enhancing its survivability against infrared homing missiles and enemy infrared search and track systems. The logical and inescapable conclusion drawn from the integration of these advanced technologies, the profound stealth of the tailless design, the persistent supersonic performance of supercruise, and the agile, all-speed control of thrust vectoring, is that the platform's primary operational mandate is the achievement of air dominance. Its design parameters are not optimized for the high payload capacity and external stores carriage typical of a multirole strike fighter or a dedicated bomber. Instead, every aspect of its configuration is refined for the singular mission of establishing and maintaining control over the aerial battlespace by detecting, engaging, and neutralizing an adversary's most capable aircraft and supporting systems. Its stealth characteristics serve as its primary defensive and offensive tool, allowing it to penetrate defended airspace and approach within weapons launch parameters without being tracked. Its supercruise capability provides the speed to dictate the timing in terms of engagement, and its advanced maneuverability ensures a high probability of success should a combat scenario devolve to a close-range encounter. The ongoing, methodical test flight program, of which recent activities form a part, is the essential process of de-risking this complex integration of technologies. Each flight is a structured experiment designed to empirically validate computational models. Expand the certified flight envelope in terms of altitude, speed, and load factor, test the performance and integration of its avionics and sensor suites, and mature the overall system's reliability. The progression from initial, short-duration flights to longer, more complex missions involving various system tests is a clear indicator of a program advancing through its developmental milestones, systematically resolving challenges and moving incrementally toward a state of operational readiness and eventual deployment.